recover 3D model from the 2D pictures. So I think it's better we talk about now. And if we have time, I will continue our discussion on the BIM IOD and also the BIM applications for pre-construction service. Okay, so let me start sharing my screen.
Professor.
Yeah.
Oh yeah.
Me and Eric still have to present our clash detection.
Okay. Yeah.
Are you okay with us just doing that now?
Sure. Yes.
Okay.
So you let me open the setting. You guys can share your screen. And meanwhile, I'm going to share the peer evaluation link in the chat box. Okay. You guys can start.
Fantastic. Can everybody see that?
Yeah, we can see it, Ryan.
All right. Fantastic.
Do you mind just zooming out a little bit on the Word document?
Yeah.
So that should be good. All right, guys. So my name is Eric, and I am presenting with Ryan. We work together on this clash detection. So I'll be doing the first 5 clashes, and then Ryan will go over the last 5. So the first clash that we found was a clash regarding a piece of equipment that was blocking a stairwell in what seems to be the steel structure. So there's not really much you can do to fix this clash because it's not really a minor interruption other than completely just redesigning that piece of equipment to go around.
Sorry to interrupt you. What's your team number?
Not too sure.
Team 1, I believe.
Undergraduate team 1?
Yes, undergraduate team 1.
Okay.
Are we good to go, Professor?
Yeah, yes, please. Sorry.
So anyways, as I was saying, the best way to resolve this clash is just to completely redesign the equipment to go around this stairwell in order to not block the function of the staircase, so that it doesn't block the walkway. So that's clash number 1. Clash number 2 we found a member connection going through a wall. And so to resolve this, we suggested that the moment connection must take the priority over the wall because it's a structural element. And so the wall should be either raised up or reconfigured in order to avoid clashing with that diagonal beam element. Clash number 3 was a member behaving contrary to the system in place. Or basically the beam is not going completely across the platform. So if you scroll down to those pictures, basically what we found is the rest of the beams in that system were behaving differently than this one particular beam for whatever reason. And so what we suggested was that either the beam member should completely span the platform or just remove the beam in order to resolve that issue. Clash number 4 was a structural member going through a wall or being interrupted by a wall. And similar to clash number 2, the structural element should take priority. And so we decided to either lower the structural system entirely to accommodate the wall or to move the wall up and out of the way of the structural connection in order to resolve this clash. And then for clash number 5, we found a structural member cutting through a conveyor system. So if you look at the picture, that blue part is a conveyor system. And then the red is a beam, a structural beam. So what we suggested was either moving the conveyor system just a few inches, I guess to the east, away from the beam so that it doesn't interrupt the structure, and the conveyor can proceed as designed. So Ryan, I'll hand it over to you.
Yeah, for clash number 6, we found another member within an enclosed wall at a corner. So for our resolution, we said to avoid it, we can either redesign the member connection or make the wall a little bit shorter to where the 2 walls intersect before the member connection. But again, the structural component is going to take precedence over the architectural. For clash number 7, we found a wall that was cutting a staircase directly in half, if you can see that down here. So our resolution would be to extend the wall a few feet to either cover the whole staircase or move it back to where the staircase is outside, whatever the design is calling for. For clash number 8, we had a wall and project component clashing. And so this piece was a pipe that was connecting to it. So what we said you could do is either move the wall or we could shorten this pipe and back this piece of equipment back this way until it had enough clearance to not be interfering with the wall. For clash number 9, we had a vertical structural member as well as some form of collector clashing. This type of clash is very difficult to deal with because it is involving a very large piece of equipment. Usually when you go to design a building, you do the bigger stuff first and then kind of fit the smaller stuff in the holes. But it's much more difficult to just move a huge piece of equipment. So we said that the structural, if it could move over a little bit, that would be the best case of action. But if not, then the entire mechanical design in that area would probably have to take a huge hit and a huge redesign. For clash number 10 and the final clash, we had a piece of mechanical equipment intersecting into a wall. Obviously, this can't happen. So we said that this is very high priority and the engineer will have to redesign the system to fit around the wall or remove the wall if there's no other solution found. And then we had one more bonus one. And this was just 2 overlapping structural members. Obviously that is not safe nor looks structurally pleasing. So we said to either shorten them to where they don't intersect each other or get rid of a structural beam entirely. But that is it.
Thank you, Ray and Eric. Any question or comment from the class? So just quick comment, I guess, you guys focus a lot on the main equipment and the structural members. So this is probably good, in the early design phase, right? So once you discover all the potential conflicts, you can notify the designers and ask them to consider some mitigation plan or some resolutions, right?
Right. And a very difficult part about these types of clashes is they happen very early in the construction phase. So if it's not figured out well before they're put in, you're talking thousands upon millions of dollars in redesign, depending on how big the project is.
Yeah.
And so using this type of software is very, very instrumental to not having those types of clashes later on down the project.
And also some of the clashes can be resolved by the contractor on the job site, such as rerouting, some kind of pipeline. It's nothing structural, right? But what do you guys discovered, critical structural members and main equipments, something that could totally affect the integrity of the project or the function of the project. So I guess it just leaves no room for the builder to make these ad hoc changes to the plan, but must go back to the designers to resolve everything, right?
Right. And especially if you ask like any engineer with their PE doing some type of structural work, their designs are usually the things that are going to trump everything else. And sometimes that's really hard on the contractor because, like you said, you can't just go in there and move something. You have to totally reconfigure your plan of attack. And again, that could cost a lot of time. That could cost a lot of money depending on the scale. But yeah, you hit it right on the head.
Yeah, and at the same time, also like you have to work with the architects because some of the clashes that we found, the easiest suggestion was just like, move it out of the way. But then that may contradict what the architect had in mind. And so it's just kind of like that balance of having to work with the engineers to provide the most ideal structure, but also working with the architect to get the aesthetic that they're looking for as well.
Yeah, I just cannot imagine the complexity of this one. Think about a product with this scale. You know, every minor change you're making will have a ripple effects. Not just architectural, but maybe other structural members, mechanical components. So just and by the way, this is a real project right now. It's going on in Vancouver, Canada, and I don't know how these guys are dealing with this real, challenges.
Right.
All right, thank you guys, thank you. Class,
Thank
please.
you, Professor.
Yeah, thank you. Please use the link I provided in the chat box and provide your evaluation. All right, so let me share my screen and start our talk on scanning. Now this one, here it is. Okay, so we're going to talk about the scanning technology. We have learned Revit. Revit is actually you designing something from nothing, but sometimes we do want to build a digital model of an existing building. Sometimes we want to have this maintenance of facility management model. Sometimes we want to have this as-built model to deliver to the future user of a building. So then that technology is called scanning. So this is our agenda today. We'll talk about scanning, different approaches for scanning, the specifications for different approaches, and also the general applications and applications in construction. Okay, so in general, the scanning we're talking about is a 3D scanning. It's a technology to scan and analyze the real world objects or environment to collect data on its geometry, the shapes, and possibly the appearance, the texture, the color of the 3D objects. The collected data then will be used to construct the digital 3D models, the digital replica of the real world structures, buildings. In general, nowadays, we have 3 types of scanning technology. Number one is a laser-based, something called LiDAR, the light detection and ranging. This technology basically uses a laser. The laser shoots out the lights, the small chunks of light pulses, and calculates how long the light will bounce back. And based on the speed of light and the travel time, so we calculate the depth information. So for scanning, for all scanning technology, the most important piece of information is the depth information, like how far away is from me. The XY is usually easier, but the depth is even more difficult. So for LiDAR, this one uses the laser to do it. So if you see my camera, I'm showing a LiDAR scanner right now on my hand. This one is, let me see where it is. Yeah, so this is actually, I don't know if you can see it from here. This one is a laser scanner, and this is a mirror that will rotate very fast. So it creates the scan in this direction. And then meanwhile, this scanner is also rotating. So in this way, it has this 360 freedom, level of freedom to scan the entire environment. So I'm going to give you a demo later. This is a LiDAR scanner. And we also have this infrared depth camera. So unlike LiDAR using the this laser to as a ranger, as a way to collect the depth information, infrared depth camera use the infrared light. So I also have this infrared light scanner in my hand. As you can see, these two are infrared lights. These 2 light bubbles are infrared lights. And this one is an infrared light camera. So this one can only check the infrared light. So, and this is a regular RGB camera, the one that captures the red, green, and blue picture. So this, you can imagine this is a regular, just a normal camera. And this is the infrared source here and the infrared camera here. And so this one will be responsible like emitting this infrared here and receiving the infrared, and calculates the time difference in this way and get the depth information. So this is a piece you can hook up on your iPad and then convert the iPad into some kind of a 3D scanner. It's very popular for the real estate industry nowadays. And the third method is the imagery method, which we call the photogrammetry. So photogrammetry is you take a lot of 2D pictures from different angles of an object. Now, just logic-wise, we should have the complete shape information from the object, the real object, because we are taking the picture from different angles. And then we have a mathematical method called structure from motion to combine and integrate all the 2D pictures and recover a 3D model from that. So that's the three categories of scanning, and both of them, all of them have their own pros and cons. The LiDAR method is the most precise and most accurate one, but it's also the most expensive one. Like for mainstream LiDAR scanner today for building scanning purpose, it can easily cost you $70,000 to $200,000. So it's much, much more expensive than a nice pickup truck. The one I have is a pretty cheap one, but it's still around 40K, 30 to 40K, like this guy. The reason is it has really good laser and also has really precise clock built in, so it can calculate calculate the travel time. And the reason it's so precise is, this little guy can send out 300,000 to 500,000 laser pulse every second. So which means, technically speaking, this one can scan and get the XYZ data of the real objects at a frequency of 300 to 500,000 data points per second. And for the high-end ones, you can easily get 2 million data points per second. So we are talking really accurate, really precise, really high resolution data from the shape. And if you can see here, the lower left of my slide, this is actually the LiDAR scanning of the Capitol building in Texas. This is in Austin, done by a research group at UT Austin. So they hired a company, they mounted this LiDAR scanner on top of a car, and they just drove on campus and built the 3D models of the entire UT Austin campus. And they call this digital twin model. It's a digital replica of the real campus. So we can easily plan out the renovation, the construction projects, traffic, and also for emergency management. This is also really good model. And this one is the same 3D model of the same building, but this one is based on the photogrammetry, the pictures. As you can see here, they just took pictures of the same building from different angles and applied a mathematical method to recover the shape. And you can see from here, the accuracy and the resolution of them are quite different. But the imagery one is really cheap, as you can imagine, because you can easily just get your phone to do it. But of course, you have to sacrifice the accuracy and the precision of your scan. And one thing you notice is everything we have from a scanning method is actually a lot of points. So the model we received from a scanner, laser scanner, infrared depth camera scanner, or imagery photogrammetry-based method, the outcome is called a point cloud model. It's a cloud of a lot of data points, and each point will have XYZ location information. So as you can see, you probably can see the pattern here on this building. That is actually the direction, how the LiDAR scanner is rotating. So basically just rotate this way for that particular second and collect a lot of XYZ information from the surface, the building, and register them. And once you have enough, of course, the shape generates. And similarly here, this is a photogrammetry, but you wouldn't see that pattern, right? And because the mathematical basis of that is quite different. So the precision, the accuracy of the infrared depth camera method is probably sit in the middle, and the cost is also around the middle. Like if you want to use this, this is a consumer version. it's around $300. You can, I don't know if you can still buy it from Amazon, maybe not, but this is around $300 solution. Imagery method is $0 because nowadays we have a lot of open source free software for you to run this photogrammetry algorithm to recover 3D model from the picture. So it's literally zero cost. And this one, like I said, can easily cost you maybe from 20K to 200K. You know, that is the reality of different scanning. So we're going to talk about how these different scanning methods work and their applications. So let me play some video quickly.
You care about center stage.
This is a movie I really like. It's the sci-fi movie Prometheus. And in this is the trailer of that.
A king has his reign. And then he dies. It's inevitable.
Prometheus has landed. These are ancient civilizations. Were separated by centuries, and yet this same pictogram was discovered at every one of them. You're smiling.
I think they want us to come and find them.
We're all here because of a map you two kids found in a cave.
Not a map. An invitation.
From whom?
Okay, so in this movie, there's a scene that they send out some drones, and the drones carry some LiDAR scanner, and they just build a 3D model of the cave in real time. As you will see in a moment.
Whatever that probe is picking up, it's reading loud.
See, they just build this, it's just happened too fast. They just build a 3D map, 3D structure map of this cave, the tunnels. Okay, so this is part of the sci-fi movie, but it was actually happening. Let me show you another video. A mining company is actually using the same technology, LiDAR scanner, to build a 3D map of the underground mining map. You guys can see this is the 3D. This is the overall view of the layout, and it's very detailed. So what they did was they put this LiDAR scanner in different scanning sites, and they combined the scanned models as a single model, which we call registration. As you can see, this was the scanner using probably this one at least worth more than $80,000. So this is critical for this company because it's a way for them to plan out their activities, but also a good way to track their productivity. So for example, if you do the scan on a weekly basis and you overlay the models, it's very easy for you to check how much progress you just made. Actually, I don't know if this one is still, oh yeah. This is the company's website. It talks about that they applied a software package to automatically calculate their Earth moving progress and convert that into a dollar value, so they can budget, they can build their owner. So great technology and great application. So let's talk about LiDAR, light detection and ranging. So what is LiDAR? You know, the principle is fairly straightforward. You have this transmitter that is sending all these very small chunks of high frequency chunks of light pulses. And when they hit the object, which we call reflector, it will bounce back. And of course, we know the speed of light, and this system also has a very precise clock built in that can count, calculate how fast it receives the bounced light. So we register this depth information. And I believe this video talks about the general principle of a LiDAR scanner.
LiDAR can be considered an acronym for light detection and ranging. It is a remote sensing technology that's used to measure distances. And it doesn't act on its own. LiDAR typically includes 3 independently operating technologies. There's the LiDAR, which is essentially a giant laser ranging device. That laser ranging device sends out millions of pulses. Today, they can send out over 400,000 pulses in 1 second. That technology gives you the distance or the range to the target. And there are 2 other technologies, GPS, which is Global Positioning System or Global Navigation Systems, that give you the location of the instrument that's holding that LiDAR sensor. And then the third technology is the Inertial Measurement Unit, which is an IMU system. And that system is used to measure the pitch, roll, and heading of for example, an airborne platform. It could also be installed on a mobile platform, like a car or a vehicle on the road. Or it could be a terrestrially mounted LiDAR system, such that it's just mounted on a tripod. And the reason why LiDAR is sometimes the preferred technology to use is that it can map the bare earth beneath vegetation better than most other technologies can.
All right, so a brief history of LiDAR. So the LiDAR technology started in the 1960s, and originally the US was using this one to map and to detect the thickness of the clouds. And by doing that, it was easier to predict the weather. So this is more for the weather forecasting. In the 1960s, we pointed to the sky. And in the 1970s, with all the missions to moon, we started to use LiDAR from the Earth to generate a 3D surface map of the moon. Of course, nowadays we also use the satellite to take a high resolution picture of that. But if you want to generate this high resolution 3D map, 3D model of the surface, so in the 1970s, we started using LiDAR to scan the surface of the moon. And in the 1980s, we just turned it around and to scan the surface of the Earth to get the model of topper surface and for different applications. And in the 1990s, this technology started to advance a lot and be more widely used in geography and also in like a traffic planning, urban planning, the LiDAR scanning, the aircraft carried LiDAR scanner using that. So going to the new century, people from the civil engineering and also from the architecture industry, they started to think about the technology, LiDAR technology used for building industry. And we just we turn it once again 90 degree, and we start to use it to model the buildings, to build a model of the buildings. And around 2010, so the driverless car started to emerge, and the first generation technology for scanning of driverless car, autonomous vehicles was actually LiDAR. I'm going to show you this quick video that how it looks like the early version of autonomous vehicle. As you can see, this is actually the real-time view from the eyes of this autonomous vehicle. It's just a LiDAR scanner. And of course, you see the shadow, right? Of course, there's occluded and the light cannot go. So it looks like a shadow. It's actually better than camera-based view because it's less affected by the light condition, by the weather, but of course, it's more expensive. I guess that's why nowadays, a lot of autonomous vehicles like Tesla, they are not using LiDAR scanner. They just use the camera view. So they use the video feed from vehicle carried the camera and applied the most advanced machine learning algorithms, computer vision to detect things and react to the scenario. But originally, LiDAR was very popular for autonomous vehicles, but fairly expensive, you kind of know that. So this is a typical LiDAR system. The components of that, it consists of a LiDAR scanner, laser scanner, of course, the laser transmitter, and the receiver of that. So together we call this a laser scanner. And also carries a high precision clock. Of course, we need a stopwatch to count like how long the light travels, right? How fast how long the light travels. So it's high precision clock. Also, we have this data storage unit built in. Pretty much for all LiDAR scanners that we have this storage built in. The data, the point cloud model data can be huge. Let's say if I'm just scanning my office, and if I scan 3 times, like I put my scanner in 3 different locations and got 3 models, combine them together, can be easily achieve 1 gigabit size, because we are talking about potentially millions of data points with XYZ information and RGB information, the texture and the color information. So we can easily have a really big sized model. That's why we also have this data storage units. Cameras, we also have these cameras built in, like for this cheap version, the camera is here outside this scanner, and inside that's a laser. So the camera is actually capturing the color and the texture information. So once this is done, we have this baking process, which means we basically paste the pieces of the pictures on top of the 3D geometry. So what you created is not just a gray 3D model, but also a 3D model with colors and textures and the appearance. IMU unit, the initial measurement unit. So basically, this one also has the IMU unit. It can sense the gesture of the current scanner, so can better correct the XYZ information to get a more accurate scan. GPS and GPS ground station are more used for the field application. So they will help you further correct the XYZ information you received. GPS ground station is something that, because you guys know how GPS works, right? So basically you have 18 to 20 something satellites, and your device will talk to them. And since the satellites know where they are and how far they are away from other satellites, so they basically triangulate the location of your device, that's GPS. But think about that, you are really far away from all the satellites. That will have some cumulated errors built in. So the GPS ground station is something you put on the ground, and the ground will self-correct itself based on the information from the satellites, and then send that further information to the device. So now your device is not only talking to the satellites flying in space far away from you, but also to some nearby ground station. So that will further improve the precision, accuracy and the precision of your GPS localization. So that information will feed into your LiDAR scanner to further correct the XYZ. So that's a typical system. In general, we have 3 types of a LiDAR scanner. So we have this static LiDAR scanner, usually sit on a tripod. Like I do have a tripod over there. I haven't got it out. And just fix that and put it on there. It's kind of like using a total station. We have the airborne laser scanner. This is more used for scanning the topper surface for the geography applications. We also have the car carried laser scanner, can be used for scanning the buildings and also for the autonomous vehicles. Like I said, the LiDAR scanner uses lights, and for regular applications, the wavelength of the lights using is a 500 nanometer to around 10,060 nanometer. And the safety, especially the eye safety, is a main concern for the LiDAR scanner. According to the regulations, the energy must be smaller than 1 microjoule or 10 to the power of -6 joule for the power. So you probably don't have a sense at how much that is. Let me tell you, like lifting an apple vertically just by 1 meter, that is 1 joule. That's already 1 million times higher energy than the laser energy in your LiDAR scanner. So it's actually very small energy that is shooting out. It's supposed to be very safe to your eye, but of course, do not stare at the LiDAR scanner while it's doing the scan. We don't know what can be the long-term impacts on you, but in general, it's fairly safe. It's according to the regulation. Okay, so depending on the wavelengths of the LiDAR scanner, we do have different application areas. So the infrared light, which is this is the spectrum of light, and going to this end, the wavelengths will become smaller and the frequency becomes higher. And going this way, the wavelengths become bigger, larger, and the frequency will become smaller. So you guys know that, right? So the frequency and the wavelengths are two characteristics of light, two reverse the characteristics of the light. So for the infrared light, which is going this way, more to the longer wavelengths from 1500 to 2000 nanometer, this is more for meteorology, Doppler LiDAR. This is more for sensing the thickness of the clouds, right? And we also have this application range near infrared from around 1000 to about 1040 to 1060 nanometer. This is more for terrestrial mapping, for the topo surface mapping. And for AEC applications, architectural and civil engineering applications, we often use the range from 700 to 1000 nanometer. And we also have the blue-green 500 to 600 nanometer. So quick question for you guys. This is a physics question. Why the wavelengths will determine the application of your LiDAR scanning area? Can anybody answer that question? So for example, for this longer wavelengths, this is more used for, scanning a bigger range, right? And this smaller wavelengths, this is more scanning like a shorter range. Why that is the case?
Because it can travel a longer distance?
Exactly, yes. So the longer wavelengths can usually travel like long distance, right? And the shorter wavelengths can usually cannot travel that long because the shorter wavelengths, usually the light will behave like particles, and they can easily be bounced back by the reflectors or any obstacles. But meanwhile, it means it's more accurate, right? So for AEC applications, we know the range we are talking about is really shorter than 1000 meters, but we do need a really good resolution. We need a good accuracy. So we actually select a shorter wavelengths, okay? But for the Doppler LiDAR, the accuracy is not that important. Precision, sorry, is not that important, but we do need the LiDAR lights to travel longer. So longer wavelengths can easily bypass a lot of obstacles and go into the cloud. That's why. Okay, so this animation shows how it works. So LiDAR basically shoots out discrete scanning, and we also have this laser pulse frequency. For example, 50K hertz means 50,000 pieces of small chunks of laser lights every second. 300 kilohertz means about 300,000. And nowadays, we do have LiDAR scanner can send out 2 million small pieces of laser light every second. And it measures the T, right? So it's kind of like here, there's a rotating mirror. The mirror is also rotating very fast, and it shoots out, small pulses of LiDAR lights. And when it hits an obstacle, it will come back. And so we register the time and we do the calculation to convert it to distance. Okay, a quick math question for the class. So if it takes 1.5 times 10 to the power of -7 seconds to receive a return pulse, what is the distance between the laser scanner and the object? And here is the speed of light. Can you guys get a calculator and do this calculation quickly? Can anybody tell me your answer?
45.
Sorry, what's your answer?
45.
45. You should divide it by 2, right? Imagine, the time you have is going away and coming back, right? So the distance you calculated should be divided by 2 because we just want that one run, not the round trip, but this one trip. Make sense?
Yeah.
Okay. So yeah, it's actually the time, travel times the speed of light divided by 2. That's what's been done inside the LiDAR scanner to get the information. Now here's the interesting question. In a survey, if the estimated minimum distance, like I'm the scanner, I'm the operator, and I just scan over, I found, oh, the minimum distance is between the object and my scanner is around 2,000 meters. Okay, then what is the maximum pulse frequency I should use? What is the maximum laser pulse sending out that small chunks of lights should I use? So here's the interesting question: why the minimum distance defines the maximum pulse frequency? Can you guys give me a quick calculation or quick explanation? Anybody? So let me give you some hint. So imagine this laser scanner sending out the pulse of light is kind of like me throwing out some balls. Okay, so I threw in some balls and I basically captured, returned the balls, and I have this watch to calculate the time, kind of like that, right? So if the distance is shorter, then guess what? Can I throw the ball faster? No, because if I throw the ball too fast, so let's say I throw this ball number 1, and without capturing the return number 1 ball, I threw this number 2 ball. Okay, now I reserve a return ball. How can I know it's returned the number 1 ball or number 2 ball? Make sense? So if I throw the ball too fast, think about that, then without capturing the returned ball, I threw another ball away. So when I receive some returned ball, there's no way for me to tell which ball is what, right? So because there's no way for me to label the lights. Then based on that, how do we determine the maximum pulse frequency based on the minimum distance? Can anybody tell me your answer? Nobody? Let me show the answer here. So basically we times 2 and divided by, the speed of light. So this 1.33 times 10 to the power of -5 is what? So for the minimum distance 2,000 meters, the travel time for my ball number 1 leaving my hand to all the way returning my hand. So that's how long it will be from leaving my hand and return to my hand, right? So the maximum frequency is the inverse of that because it's 75,000 balls per second. Because if I'm throwing faster than that, then when I throw the second ball, the first ball hasn't returned, hasn't had enough time to return to my hand. Make sense? So which means for this case, if I'm scanning some room of some structure, open area, then the minimum distance is 2,000 meters, and the maximum frequency I should use is only around 75 kHz. Make sense, guys? You guys have any question, comments? No. So it means that for a scan task, you have to adjust the parameters of scanner. Earlier the scanners, the operators do have this menu, and based on the menu, it's kind of like a table telling you the best practice and the numbers that you should set up on a scanner based on the scan task and the environment. Fortunately, nowadays, these scanners are becoming smarter, and they do have some building algorithms to discard, to abandon some points when they sense that the room is too small or the room is too large. Make sense? So the key point here, guys, is the distance, the environment you are scanning will affect the best scan frequency, the LiDAR frequency you are using. Okay. I guess that's so quiet. All right. So, and we have some performance metrics for LiDAR scanner. Like I said, you know, the outcome is point cloud. Point cloud is a densely spaced network of highly accurate points in this XYZ system. So we have two important metrics to evaluate the performance of your scan. One is accuracy, one is precision. Precision is also resolution. So accuracy, let me ask this question. Is 1 inch always more accurate than 1 feet? Anybody? Is 1 inch always more accurate than 1 foot?
Yes.
Then think about that. If I'm scanning like just my table, then 1 inch arrow is significant. And if I'm scanning the stadium, you know, of UF stadium, then 1 foot is not that significant. Make sense? So the arrow is actually relative. It's relative of the size and the scale of your scan. So that's why, according to NMAS and NSSDA, so let me check their full name. I always forgot their name. NMAS. It's the national, no. Yeah, National Mutual Aid System. Let me check the NSSDA. And it's a national standard for spatial data accuracy. You know, that's all the national standard. So according to their standard, the accuracy is actually measured as a scale. You know, this is different scale, and this is actually what we call the CMMS 90%, which is the 90% confidence interval of accuracy. This one shows the 95% confidence interval of your accuracy. So the bigger, the better. And it shows that for the scale, which means 1 inch in your final model is actually 100 feet in the real object, or 1/1200. If the scale is like this, then to achieve a 95% accuracy, you should have an arrow lower than 3.8 feet. But if your scale is, let's say, 1/24,000, you know, that's a bigger scale, right? Then to achieve the same level of accuracy, 95% confidence level, the arrow can be as high as 45 feet. Now I got the point. So basically, we want to achieve certain level for confidence level, and so the standards give you the arrow you can have, giving the scale in your scan. Make sense? Scanning bigger things, scanning smaller things, that means different things. The math different accuracy, absolute accuracy numbers. So precision is the number of data points per meter, or the data spacing, like how dense your data is, the resolution of your data. Similar question, is 3 centimeter spacing always more precise than 30 centimeter? Guys?
No.
No, once again, this depends on the scale, right? So if I'm scanning my table, 3 centimeter, you know, is this much. Probably if my resolution is 3 centimeter, my scan probably just totally lose half of my cell phone. But if I'm scanning well hall, then 30 centimeter is okay, it's acceptable. So it also depends on the scale. And by the way, we do have regulations to define, you know, the precision, the required precision as well. By the way, the resolution is a critical factor for the scanning operator to consider as well. If you are a mechanical engineer, and 30 centimeter, is that good? No, because we do have a lot of AC terminals, like window ACs. That is usually right around the size of a 30 centimeter. I actually there was a guest speaker, and he gave us a real case that they mistakenly adjusted the parameters of their scan, and it's actually larger than the size of a lot of window AC units, and they just totally lost a lot of useful information to count the numbers of AC units because it's right smaller, it's right below the resolution they were using. So this, determining the right accuracy, determining the right precision, and also determining the right scanning frequency are all critical for you to make a good decision scanning planning. And this one shows, like a different resolution, how that can be visualized in terms of the airborne scanning. As you can see, this is the base location. What is the base location? So basically, for most of the survey, we do have this reference system that we have some points that showing very accurate numbers, XYZ. So for the traditional survey, we just use the survey. What's the name of the survey device? I forgot the name. Did you guys take the course that you use the survey device? Is more kind of like a telescope, and you have the ruler to document the elevation. I forgot the name, sorry. So anyway, we use the survey device, and we just basically follow the line all the way to the target. So we basically just convert or transfer the most accurate measure to my current measure. This is how it works. And like this, let's see this red line. And this is a 30-meter precision, how it looks like. This is 10-meter precision, how it looks like. And this is 2-meter. So these are all manual survey result. And this is a LiDAR survey result. You can see the level of details and the information captured by that, by increasing the precision is very important. And also, we have this multiple return LiDAR scanner. So in this way, the receiver of the laser scanner can register multiple returns from the same scan. And this is particularly useful for agriculture. So if you want to use a LiDAR scanner to check the growth, the status of the plants, to check the trees, and so we can use this one to register multi-return, and use this like for example, the distance, the delta between this return and this return to calculate the size of the tree and also the size of the plants. So this is also this is very popular and very useful for the agriculture industry. This is called a multiple return LiDAR. And then there's another thing that is fairly important for the LiDAR scanner is the field of view, or FOV, something that you can also plan. So the field of view actually related to a beam divergence is the size. You can imagine, like for airborne scanner, LiDAR scanner, this is a cylinder you are using. So the bigger the cylinder is, means the scanning will be more efficient, it will be faster. But of course, you will be losing some useful information since you're scanning too fast, or the field of view is too big. So depending on your purpose, if I'm doing this very precise traffic flow scanning, then you have to shrink the FOV. But if I'm doing a general topper surface modeling, then of course you can increase the field of view. So this is another parameters. And yeah, this is another view of the entire LiDAR scanning system. We have this LiDAR scanner built in, the clock, the IMU to correct the pose of the scanner. We have the GPS and the GPS base station, ground station to further correct, the position of the scanner and to get a more accurate result. This is how the data from a LiDAR scanner is processed. So first we get the raw data. As you can see, all the yellow points are the raw data. So the data with XY information also, and also the range information, the depth information. And then we connect the neighboring data points into a lot of small triangles. Why small triangles? Because ultimately, we don't just want the point cloud model. We want the shape of that. We want the surface. So we are using a lot of small triangles to simulate the surface of a 3D object. And so a lot of small triangles is called a team. This is a team model. This is a triangulated irregular network. So it looks like a network. And the purpose we are doing this is to get the surface, to simulate the surface of the 3D object. So this is called a team model. And for each vertex or the corner of the small triangle, we have the XYZ information. Since this one is for, the topper surface simulation, so it only shows the elevation of that, like 165 meter, 165.39 meter. So this is how it looks like. But if we want to get a more precise model, we need multiple points. Can we, instead of having additional scan and get a more precise, get a better, higher resolution? Yes, we do the interpolation. So this raw model with the elevation information is called a DEM, digital elevation models. But then we just mathematically interpolate, for example, from this 165.45 to this 165.42. I just assume the change of the slope just goes linearly, so I actually get the elevation for those points. Those are the dummy points, not from my scan, but from my calculation. So I create another model, dense model called a raster model. So this model is called a raster model. So you will probably hear team, DEM, and raster. That's how it comes. And this one shows how a DEM model and a raster model can be different. So this is actually the model without interpolation, but this is the model with interpolation. You can see more details are reviewed. So in terms of LiDAR application, terrain mapping, it's very popular today. And this is archaeology. This is an interesting story. They discovered Asian civilization in South America. From the satellite image, you wouldn't see anything, but they thought there must be some civilization there, but they just didn't have the evidence. So they had this airborne LiDAR flag there, and they used the multiple return LiDAR. So basically, they registered the trees, and they just used the computer to remove the trees. And guess what happened? They found this python on the ground. Looks like some man-made structure. So they sent a group of people there, and they found that Asian civilization. This is the story. So this is an interesting application of LiDAR. And this one, like I said, the LiDAR application can be used to track the pergolas automatically. Like in this way, in this case, they overlay two LiDAR scanner models together, and the color code difference. By checking how much changes happened, they can convert that into dollar amount or effort amount. And of course, LiDAR scanner is also has been used for the autonomous vehicles. But I have seen nowadays, a lot of companies switch to this pure imagery based method. So that's a LiDAR scanner. Any questions so far?
Yes, Professor, I have a question.
Yeah.
When Apple announced the last iPhone, I believe I saw like LiDAR on iPhone. Is it different from this one?
That's a LiDAR scanner, but of course they have different capabilities. What iPhone is using is actually a very small LiDAR scanner. The frequency and the range of that is much smaller than the professional ones, including this one, because the application is more for a room size scan, for AR application, augmented reality application, and for better face recognition. So yes, to answer your question, that's a LiDAR scanner. And Apple is actually using multiple technologies. I'm not using the latest version of iPhone, but this one, what do they call the Face ID? That's actually, let me see if I can show you that. I don't know if this is flashing on my camera, I guess. Can you see that?
Yes, yes.
That's actually infrared light. So this is an infrared light ranger, kind of like this guy. So Apple is using that, but Apple is also using, like, even without the LiDAR scanner, I can use my phone to scan the environment, and I can use my phone for the AR application, like a ruler to measure distance. That is a photogrammetry, because in order to measure the distance with a camera, you have to build a 3D model first and then measure that. And also nowadays the iPhone 12 also has the LiDAR scanner. So actually iPhone, the latest iPhone is using all three scanning technologies together. LiDAR scanner, infrared light based ranger, and photogrammetry. Other questions? Okay, so if no question, let's take a brief break, 5-minute break. Let's return 5:15. Okay.